Ô, Bárbara, olha o cantinho de café que eu trouxe aqui, ó.
Ah, trouxe café, então. Então, você pode dormir. Tem gente chegando aqui.
I'll just check the voice on the YouTube first.
And it's fine?
And just check it.
Eu não vou sentar, pode resolver. All right.
Yeah, we have the audio.
To delete. Agora, ele... Ah, não. Yes. Yes. Ah, então nem adiantava trazer o teu mostrador.
Eu tenho aqui no Play. Quem está assistindo online não consigo.
Okay, start. So hello everyone, welcome back to Wednesday seminars. So today we have Dr. Barbara Castanheira with us. So she was born and raised in Brazil. She earned her BSc, MSc and PhD from UFRGS. She earned a prized fellowship as an excellent student during her PhD at UT Austin. From 2007 to 10, she was a postdoc researcher at University of Vienna, Austin. She returned to Texas as a postdoc researcher and a Department of Astronomy at the University of Texas at Austin in 2011, where she still keeps her researcher status and affiliation. In 2016, she joined Baylor University as full-time lecturer. In summer 2023, she started as a tenure-track assistant professor. So, without any further ado, let's welcome Dr. Barbara for her lecture.
Thank you. So today I'm going to talk to you folks about white dwarfs in the HETDEX survey. And in astronomy, we have the luxury to put pretty pictures every time that we give a talk. Unfortunately, the pretty pictures of white dwarfs are not necessarily very pretty. So they are very, underwhelming, for say the least. But I can put in here the next best thing, which is a picture from a pre-white dwarf. So this was taken with the James Webb Space Telescope, and this is a planetary nebula just before the white dwarf is formed. So we see here the ejecta of the outer layers. But what's left here will become eventually a white dwarf. I was happy to see this picture as one of the first releases of images that came around from the James Webb Space Telescope. So to start our story today, let's talk about why white dwarfs are important. And we have seen this picture this diagram many times. This is not to scale. And this represents the stellar evolution for single stars. And what matters most here is the mass. And mass is the major physical quantity that will dictate how things or how stars will evolve. If a star is a small mass, give or take up to 10 solar masses, it's obviously very model dependent, roughly between 8.5 and 10 point something. It will follow this path here, and it will end its lifetime as a white dwarf. And this represents the evolution of more than 95% of all single stars. I don't need to argue with you that understanding the structure of the stars will become very important because it places incredible constraints when we are modeling the evolution of stars. But the more spectacular path happens when the stars are big and they are born very, very large. So in this path here, which I cannot point with my hand, according to Anna, but with the mouse here, in this lower path here, the stars will evolve and undergo supernova events. And what's left over is a neutron star, black hole, or nothing. And this, of course, is a much more complicated evolutionary phase. The stars in the high mass stars will lose a whole lot of mass, changing how the stars will evolve. Now, needless to say, this is one of my favorite images in astronomy, and it has been my favorite image, the pillars of creation. Just a side note, I really, really like the one from Hubble Space Telescope, but this one is the updated version from James Webb, showing to us here a nursery of stars. So each one of those bright points here will eventually condense and form stars. And even for an untrained eye, we can see here that stars are not born isolated. So stars are most of the times born in binary systems. And of course, in binary systems, what happens is the stars can become a red giant and pass through stellar evolutionary phases, and they will eventually exchange mass. And by exchanging mass, it will change how the stars will evolve. This here is a cartoon representation of a cataclysmic variable. So we have here a white dwarf and the donor star, and we have this formation of this accretion disk. And depending on how much mass is transferred to the white dwarf, we can have nova events, we can have supernova events, we can have nothing happen, we can have a formation of a whole lot of things. It is possible even in interacting systems, those are called interacting systems, that we have the formation of planets, second generation planets. Okay, so those are more complicated mechanisms, but I'm so sorry. That was a fast interruption. Sorry, nobody knows me here. It's okay. So I'm a firm believer that we have seen planets more and more around stars, and I'm a firm believer that it's very, very easy to form planets. And even the more recent models are pointing towards the fact that it's so, I mean, we know that for microscopic levels, it's very easy. And even when you have pebble sizes, they stick together more than we thought. We thought that the planetesimal, the core accretion, would actually be something more destructive and more disruptive, but they don't need to necessarily collide. They need just to stick together and form those resonance things, and matter will just fall into them. So that's again a side note on the possible formation of second generation planets. But again, if stars are in binary systems, and this is the best model scenario to explain to us the supernova type 1a. And we have here, obviously, this is just a tiny, tiny portion of the representation of binary evolution, but we can have here closed binaries, and sorry about that. And they're forming here a common envelope, and we can have a common envelope. We can have a double degenerate scenario here, that we have a merger. We can have a single white dwarf. We can have two white dwarfs merging together. So lots of different scenarios that can happen. And this, so far, is the best model to explain the supernova type 1a. Now, you folks from extragalactic might be, oh, yeah, so you heard about the supernova type 1a, and they are becoming very, very important because of being standard candles. And this is just to show the difference between the light curves of the stars that will come, the supernovas that will come from the massive stars, which are the colored ones here. I find it very interesting, this plateau, light curves and all sorts of shapes. But the supernova type 1a has a very, very distinct shape. And it's visible for a short period of time, just a few weeks, and it can be as bright as a small galaxy. So for you folks trying to determine distances of extragalactic stuff, this becomes very, very important. And it was, again, we can scale down. This is just from, sorry, I will skip this. We can scale this down here to try to figure out the distance. And we are talking in the ladder distances somewhere here, I think. No clusters, no, here, the supernova type 1a. Now, it was also with the discovery of the supernova type 1a that this new ingredient for the universe was proposed. And this new ingredient is the dark energy. So what we have been observing is that since the time of Hubble, that the nearby galaxies move further away from us, and the further they are, they move faster from us, right? But we observed this kick on the expansion of the universe, so there is an acceleration, and this was actually discovered by the observation of the supernova as independent methods to determine the distances. So, so this is just a plot showing the observed magnitude and the redshift of those galaxies, which is proportional or related to the distance, but not quite the distance. So dark energy becomes an interesting ingredient. And I wanted to say up to 10 years ago, there have been several models that were proposed to explain the observable universe and trying to use different methods, but general relativity has been surviving all those tests, including gravitational waves, the observation of gravitational waves, the observation of the black hole and the event horizon and so on. So actually dark energy is still an ingredient necessary to explain, according to our best models here, in the universe. So the idea of HETDEX is a survey that was proposed to probe dark energy, to try to observe that. And this diagram here, which again, it's, gosh, I'm losing my mouse here, sorry. This here. So this is the beginning of the universe that we can observe, right? So it's radiation dominated, and then it becomes matter dominated, and up to where we are now, it will become dark energy dominated. So the idea here is that right now, our universe is contains more than 75% of the energy of the universe. And this is the redshift, 0.4, about 10 gigayears, when dark energy becomes important or more relevant to determine the fate of the universe. This is just one of those models here showing the differences between a coasting and accelerating universe. So this would be a universe with dark energy as one of the ingredients. We know, for example, that this decelerating the Big Crunch is probably not the fate of our current universe, right? So, but I just put it here, those models, just for completeness. So all this thing here to talk to you folks about dark energy, I just find it interesting to always go back and here for the students, for the young students, always look into the original papers. It's very, very interesting and a very cool exercise to do. So this is a picture from Hubble, the original paper of Hubble observing the recession velocity in comparison to the distances of the nearby galaxies. And what Hubble observed, Hubble the person, not the telescopes, like Kepler the person, not the telescope. Hubble the person, Hubble the astronomer observed was this here, coming from the measurements from us moving outwards. And interestingly, and I find this again back to the original ideas here, when you look at the observations from the cosmic background radiation, the cosmic microwave background, and we see the observations from there to us, right? There's clearly here a relationship between velocity and distance, and we really can attempt to extrapolate that, and we look at the recession velocity redshift of those galaxies, and was like, oh, that's the distance, that's the distance. Well, it turns out that those two measurements from us that way and from that way from the beginning of the universe to us, they agreed much better in the past. And nowadays we have this major disagreement with respect to this relationship to the Hubble constant. So this is the value of the Hubble constant as a function of the year determined by different methods. So here from the red one here is from the observation of the galaxies, extrapolating the velocity of the galaxies, the nearby the distances and the velocities, and then from the cosmic background radiation. And I found it interesting for us to see that those two methods used to agree much better, despite the error bars were this big, and nowadays we were able to make the error bars much smaller, and they are disagreeing much more. So I'm not necessarily selling to you dark energy as the answer to explain the universe or to say, hey, we know very well. I think there is a lot of research that can be done in both fields to try. I mean, it shouldn't be different, right? We should get a good agreement in our description, but understanding the models, understanding the limitations of the models that we have will actually help us better describe the universe as we observe. So the HETDEX is the HET dark energy experiment, and just like many other experiments, it was set to probe dark energy. And they target Lyman alpha galaxies. Those are, this is a spectrum here of Lyman alpha galaxies. My understanding is they chose those galaxies because they're very abundant. It doesn't matter where you look, they are all there, right? So that's pretty easy. Fortunately, so they actually planned 14,000 hours in dark time for 7 years. They built this instrument called Virus, and the wavelength is 3,500 to 5,500 angstroms. So in the visible, because those galaxies are very redshifted, not incredibly, but just a little bit. In one shot, they take more than 3,000 spectra, very low resolution, about 2 angstroms, and they have an exposure time of 2 angstroms, and 18 minutes in dark time. This picture here of the moon, and this is the field of view that they upgraded the HETDEX, this instrument here. So they used a telescope called AGT, or Hobby Eberly telescope. It is located at McDonald Observatory, and it's a very interesting design. If you folks have seen a real telescope, I'm going to point over there. How do? We move the telescope here, we align the altitude here, and we're able to point the telescope right there. This telescope has a fixed mount, and it only rotates like this. So if I want to observe there, I point this part of the mirror, the primary mirror, and the tracker follows the stars. So that reduces the cost of the telescope to about 15–20% of the actual cost of a fully movable telescope, if you will. But of course, you have the drawback that you can only access the stars when they are rising and when they are setting. So you can get the targets every night for 45 minutes and 45 more minutes here. So we have a reduction on the accessibility of the sky as a whole. But anyways, it becomes a much, much cheaper telescope. So that was what they sold, basically. The primary mirror has this size here, 11 meters, huge, huge, huge mirror. And it has a 9.2 effective aperture. And I will talk to you folks a little bit about that, because when we talk about spectroscopy, this is becoming a little bit more challenging. It's a segmented mirror, so 91 mirrors, blah, blah, blah. And of course, you can imagine that you don't send astronomers to observe at the HET. It's a queue schedule. It was immediately from the design point, because they access and they observe multiple programs every night. So they have resident astronomers. For people graduating in the future, if you like telescopes, that's a very, very interesting place to live, in the middle of nowhere, West Texas. Yeah. So this here is a picture I took from the HET, and this is the primary mirror. It is literally a bucket of photons, okay? And this here is the tracker, and you can see this diagram shows a little bit better. That's the diagram showing this optical fiber cables, these green cables here that go and feed into the tracker up there. And this here is what actually moves. On the sides, we have the cages where they put this instrument virus. And virus, I promise you folks, it was way before the pandemic. A virus is a visual, integral, replicable units, spectrograph, because you could make many of them and replicate them. They were much more creative before 2020. They had the reduction was cure, and then they had vaccine, and then yeah, they did change those names afterwards. It became a little touchy subject, obviously. But they built those instruments, so lots and lots of spectrographs, and it was a very interesting design here. I'm not sure if you can see very well here on the bottom. You see this green here. So this is basically to make sure that all the mirrors are perfectly aligned, and yeah, so it's a very interesting design. HET was the model for salt, so somehow successful, has many problems. I heard that salt has their own problems, but yes, it's very interesting. So the field of observations for HETDEX, they had two fields, the spring and the fall field. You send me the coordinates later, so that's where we can look what we have observed here. And they are looking for galaxies, okay? This is in galactic coordinates, sorry. And here I plot also the objects that were in HETDEX, the black ones, and then we have here Gaia information. So we have the stars that were also there. So the detectors is optical fibers, and gosh, it didn't go yet. Oops.
Where are the fields like when we didn't get it? Is this thing red?
Yes, yeah. So that
Red and black.
yeah, I personally prefer looking in array and DAC, but yeah, it's not going. Stuck. Well,
Maybe you can use these as well.
okay.
It's somehow disconnected.
I disconnected myself.
So virus.
It's a virus, a different one, another dead joke. Another dead joke. Yes. All right.
Okay, now.
Thank you, Anna. Okay. Okay. Did it go? Yeah. So this is the representation of the fibers. And here we see on the side here, each one of the spectra, I mean, cannot see them individual, but there's a lot of spectra that fall into the fibers here. So those are the 448 fibers, and here's the representation of the detectors. This here is another instrument that they built before the virus, which was the virus P, or the prototype. And you can see, I mean, I'm not sure if you can tell here, but I'll tell you that the fibers are a little bit further apart, but that was the testing of this whole virus instrument here. And this is the reconstructed image. So this was it is a sub-dwarf. And I've done a lot of those extractions from the fibers that individually. And the problem is you need to make sure that you sample the whole object, not only one part, right? Otherwise, we end up having more red light or more blue light. So that becomes a little bit of a problem. So you have to combine all the fibers that will contain all the image to get the correct calibration here for the stars. For HETDEX, for the virus instrument, we actually have to, they computed that to make a Richter pattern of 3 times 3 exposures. So that's why 18 minutes, so 6 minutes, 6 minutes, and 6 minutes. And they have a completeness pretty acceptable. It's not perfect, but it's as good as they managed to design the whole instrument. And that's why it becomes a very uniform survey. And it's pretty nice to have all this information. So again, they were targeting Lyman alpha galaxies, but everything that fell into the fibers got spectra. And the main survey knew about those objects and already engaged other astronomers to try and use the data to leverage this survey, not only to become a dark energy survey, but to become a stellar survey, which is what we end up doing here. So this is they trained here to try to find similarities. So this would be using some sort of machine learning, and we can look for group the stars by similarities, basically. So we have here in the top diagram, in terms of temperature. So this region would be the cold stars, and this would be the hotter stars. In this program here that I published with Keith Hawkins, we were looking for the metal poor stars. So you can look for metallicities, you can look for, sizes of stars or temperature and so on. This is the diagram of the signal to noise. So it becomes not great, but we do as we get fainter. So this would be the fainter end. But this survey will go up to magnitude 21, 22, and we get spectra for free. We know how long it takes in Gemini time to get this, how long of our time takes to write a proposal to do that. I'm getting all this data for free. It's just amazing. This is my favorite plot of all plots that I have seen here. So basically, those are the stars of HETDEX, and this was the data released too. And what we have done here was basically group them by spectral type. And here we have from the M stars all the way to the white dwarfs here on this left lower corner, and they are represented here on top. Not only the A's, I promise, not only the ones with hydrogen lines, but we've seen other stars as well. But this is one of the, so all those stars were there. We can also look for white dwarfs based on the photometry alone. So I have been looking if we don't have Gaia data, because the survey talking about stars, there are 21, 22 magnitudes. You start becoming very, very thin, the amount of available stuff that we can get from Sloan Digital Sky Survey or from Gaia. So we have to be very creative and try to figure out where are the white dwarfs and so on. I marked here in this diagram, which is a color. So this is done with this Sloan data. And this line here and those blue dots represent where the white dwarfs are. So we have to make sure that you can try to cross-match as many catalogs as we possibly can. And of course, Gaia is basically the one that our go-to survey to cross-match. This shows an HR diagram and the position of the white dwarfs here. Just if you are not a stellar astronomer, you are not necessarily super familiar with Gaia data, but if you are, nowadays they have 1.4 billion stars. So this is just like you have to put your data on Gaia and try to figure out what are the quantities for the stars. So this is one of the examples of a star that one of those free spectra that we got. Again, the magnitude of Gaia magnitude is 19.8, 20 for free. It's trash for them. I just find this amazingly beautiful. So in this here, we fit the spectra 2 ways. So we fit here the whole spectrum. And right here, I use the distance information and some models from the radius. Because we have to, again, understand how the models are calculated and how the data is produced to us. The models are calculated the flux at the surface of the star. It's a point on the surface of the star that has that value of flux. The data that comes to us, it's integrated over the surface disk of the star and traveled all the distance to reach our planet. So they're completely different scales, right? Different values. So one way to think about comparing observations and models would be, well, let's basically try and normalize the spectrum, right? It's probably just a problem of normalization. And again, a simplistic idea of comparing models to data, and if you took mathematical methods in these classes, you learn how difficult this is. You have to make many choices. And one choice would be in terms of the normalization. Where do you normalize? So an untrained eye would immediately say, well, let's avoid the hydrogen lines here, the Balmer lines, which makes sense. But if I go to a place right here or right here to try and normalize, if I choose this lower point or the upper point, or if I do something different, I end up changing the flux or the black body of the spectrum, and I'm going to get the wrong temperature. So this is not as simple as simply comparing models to the data, right? So you have to make sure that you add maybe the photometric values here. But in our case, this spectrum here is so small in wavelength, the range is so small that we don't have many points in the black body curve to put here to constrain this. So I think I have 2 points of photometry that I can use, and one is more sample than the other. So again, it's not as simple as it looks, as simply, oh, let me compare this database with that. So I attempted to do something different here, and we were getting very close values when we compared that. So with an external uncertainty of 200, 300 Kelvin by choosing one method and versus the other. So that was what we chose to do. One interesting thing that I want to show to you folks is, and encourage everybody to engage on other surveys, is what can you contribute when you leverage a survey? And people think, oh, white dwarfs are just boring, and yeah, who cares about them? Not spectacular. Kepler already learned everything that we needed to know, right? He has all these students when there is nothing else to know, and so on. So we started looking at the data, and this is before the data release happened to the public. And let me just flip it again here. And I want you to look at this part of the spectrum here. Look at this. And I saw it, and I'm like, oh, but there's one here that has this little hump. This is completely artificial. So that was a problem on the calibration of the main survey. So we helped them. I was like so happy. I was like, I'm useful. Finally, finally useful to something. So just to compare here, this is another survey. This is the Sloan Digital Sky Survey, and they did have a spectral resolution a little bit higher than ours, but also a spectral coverage much, much longer than the ones from HETDEX. So what the HETDEX tried to do is to calibrate the flux in a better way. So let's see if we are doing a good job with our flux calibration. I'm going to say this once again. I'm pointing that bucket to collect photons over there, but when the star is right here, the size of the telescope is smaller than when the star is right here. So the apparent or the actual aperture of the telescope changes throughout the observation. So you have to do a flux calibration of the stars that fall into the field as we are observing. So it's not a simple task as just say, oh, let me observe a standard star and get this out of this, spit it out and blah, blah. No, you have to do a full flux calibration and so on. So one of those sanity checks that they have done was compare different spectral types with data from Sloan. And this top panel here in the middle is a white dwarf, and the red one is the Sloan data, and the black one is the HETDEX. There is nothing in that ultraviolet part. So we had to use the white dwarfs to recalibrate the whole survey. So we derived a full function for the hundreds of white dwarfs that we found to do a further, they call it dust correction, but it's not dust, but it's something like that. But that was like a very, very interesting part of our contribution as well. And just to remind you, we are talking about wavelengths that are right here, very close to the atmospheric cutoff. So we have, on top of that, the efficiency of the spectrographs. The mirror is not optimized to ultraviolet, nothing. So we have, you know, to make sure that this whole calibration is well designed.
Desculpa, Bárbara.
Yes.
O problema da projeção da parte do céu sobre o telescópio deve ser corrigido automaticamente? Ou
Corrige, é.
tu conhece tudo praticamente? Né?
Eu não conheço tudo. Tem a força.
Digo, tudo como o tamanho da
Sim.
direção em conta a
Sim,
estrela, conhece qual é o fator.
Sim, então eles têm um fator de
Mas mesmo assim,
ainda tem um problema porque tem a correção atmosférica, tem a sensibilidade dos CCDs e de tudo, né? Que não é totalmente otimizado, mas eles têm o header das observações, é uma coisa quilométrica, porque muda muito, né? Apesar de ser uniforme, tem essa não uniformidade, né? É um baita de um header, bem divertido de olhar esses dados, mas tem que lidar. Yeah. So what did we do with most of the stars of the survey? So we were fitting the spectra of the stars. I mentioned that I was not going to show you any white dwarfs, but here it is. There's a blue dot here. That's the boring white dwarf that I was not going to show necessarily. And we did also fit using spectroscopy, so basically fitting the spectra. We fit the colors that we have from Sloan data, so the U, G, R, I, and Z. And here, for example, for this particular star, we have the distance determined by Gaia. That's the absolute magnitude and the value for effective temperature from spectroscopy, and the effective temperature from photometry. So it's in the ballpark, right? It's not to the dots, but it's on the ballpark. You know, it's we were confident that we are doing a decent job in analyzing the data. Now, one interesting thing that showed up in the survey was I'm very used to look up those stars on Sloan and find those pretty blue dots here, and I found some purple ones. And then, of course, we see here that that's actually the image copy and paste from the Sloan from the survey. And I was like, well, okay. And I look at the spectra and I see this little thing here, which is a little hump, a little reddening on the spectrum. And in our sample, we had 10% of our stars had this little reddening in the spectrum. And we were like, for a few of them, we were able to get the spectra from Sloan. And in this case here, we have the black body, as you can see here, the white dwarf. And this is a companion, so probably an M dwarf as well. So I was talking to Kepler and to Elindo and to Larissa a couple of days ago, or yesterday, and we were discussing the fact that whether this reddening is a member of it's a binary, a companion, or not, because once again we have to use the fact that you are not looking into the plane of the galaxy, but we are looking perpendicular to the plane of the galaxy. This is the extragalactic survey. So it's possible that we are catching something in the line of sight and not necessarily a companion from the star. So this is another thing that we need to disentangle, right? And of course, if you had multiple spectra, we can see the shift of the lines, detect binaries. But in this case, from one spectra, we have to see how much of the flux is coming from the white dwarf and how much of the flux is coming from the other one before going ahead and applying for time and telescope time and so on. But this was very interesting. I have a student working on this part here, is actually looking to place some limits to see maybe we can see disks, maybe we can see some. Ideally, if we have really, really good spectral university planets, right? But we don't have it here, that we're not to that precision yet, but it's pointing towards this, this direction as well. So one of the major goals of our survey is to actually try to study white dwarfs as an ensemble and try to contribute to the white dwarf luminosity function. So this is one of those plots, and it's if you've never seen this here, so don't worry so much about the unit here, but this represents the number of the white dwarfs that we have, and those bins here are bins of brightness. So here are the brighter ones and the fainter and the fainter and the fainter ones. So our goal is to use surveys such as HETDEX and even fainter surveys to try and contribute in these bins right here to try to make sure that we know how old a particular component of our galaxy is. If we had enough data, imagine that, we would be able to disentangle the disks, the thin disk, the thick disk, even components of the halo, and try to make sure that you decrease here the uncertainty. But of course, those uncertainties are nearly intrinsic from the fact that those objects become very, very faint as well. But this is one of our ultimate goals, to try to use white dwarfs. And I'm old enough to remember that in the old days, the white dwarfs are always pointing towards the lower end of the values of the age of the universe, right? Or the age of globular clusters and so on. And they actually had to meet somewhere, right? That was an interesting, yeah. Anyways, I also do a lot of pulsating white dwarfs, so this is something very close and dear to my heart, since this was part of my PhD thesis. And the only way to know that, how do we know that this table is made of wood and not plastic painted with wood? You knock on the table, and if you can see the sound that propagates here, will tell us that this table is more likely made of wood than made of plastic. The only way to probe the interior of stars is if you have pulsation periods and match the pulsation periods to the models, because just like in a musical instrument, the frequencies that are trapped within a certain cavity, which would be the internal structure of the stars, will tell us how much of that there is. This is a nature diagram done by one of my very good friends, Gerald Handler, showing here the position of all the instability strips. So fortunately for us, the stars pulsate in all phases that we have. And this is the white dwarf cooling sequence. So when we determine the temperature and gravity of the white dwarfs, you can go to the telescope and look for variables. And we attempted to do that using this telescope, the 2.1 meter telescope, also at McDonald Observatory. Here is a picture of my students all the way up there. I have a heart attack every time they go all the way up there. Don't let them go anymore. But this is the telescope that we used. And within the HETDEX survey, we searched for some of those variables here. And yes, I sent a student to observe, and there was a lot of clouds and so on, so the data is very small. So we don't know if this is a variable or not. So this is the representation of the light curve, and down here is the Fourier transform. So we will need to have a signal about 3 to 4 times this noise level, and this I'm not confident enough to say that this is a variable or not. So he looked into 2 different ones. This is even worse than the previous one. But yeah, so we have several components that we try to look for those for those stars. So I just ended this here with a picture I took many, many months ago. And a saying from the first director of McDonald Observatory, saying that one of the first tasks to be undertaken by the staff at McDonald Observatory will be to investigate further the mysteries of the white dwarfs. And this was said in 1939. I'm hoping I'm still giving this talk in 2039. Maybe it's going to be 100 years. So I thank you very much, everybody, for coming. My old professors, my old colleagues, and my new future collaborators. Thank you, and I'm open for questions.
Thank you for the insightful talk. So any questions? Yes.
Thank you for the, nice to hear virus P, all these things that, yeah, I've learned from the galaxy's perspective. So I have a few questions. First one, what are the prospects with LSST that you're planning, are you planning to do because you saw that it was not really good to do the variability, but you're gonna get this for free.
For free, exactly. I'm always looking for free stuff, yes. Yeah, the LSST, we will need to make sure that we get the short-term variabilities because the major problem is the time scales of pulsations of white dwarfs. They're very, very short. Some of them are very, very short. So we need that's one of
How
so the minimum, typically the minimum is like 200 seconds. So then we need to be creative enough to do that. But there are other things that we can learn, even if the time scales are not that short. We can learn about rotation rates. We can learn about, orbital periods, if we have other time scales. But yeah.
Are you
LSST
working
would
with
be
brokers? Are you working with any brokers to get the learnings?
No, I'm more involved into Roman, which is gonna have, I'm a little bit, I think it will be a little bit more challenging because of the ramp detectors that they keep on reading as they saturate, and so how to disentangle that information, that's what I'm looking more, because if you can ask for shorter, and you can set how fast do you want to read the data that's coming, but yeah. But no, LSST, I haven't personally not involved, but yeah, it's exciting as well.
Any more questions? Yes.
How many white dwarfs have been discovered so far?
That is a very good
I
question.
know because my student asked the other day, I didn't know, I said, 20,000.
So Kepler, that me personally have discovered, or that we collectively, the royal way, the number is 50,000, yeah.
How
The
many with
me here on this survey, we have brand new 600.
You know, I'm the total, and with mass determined.
But me, 39,000.
Wow.
Yeah.
The numbers, the royals, there's some.
Someone else that question?
But it's a bit, it's entertaining to cross match catalogs. We were doing this yesterday. I'm like, how do we do this? Matching is fun, but yeah. So
Yes, Ajay.
So thanks, Barbara, very nice talk. So trash for you is good for us. What are you doing with the agents?
oh yes, yes, they actually have a working group of the AGNs, and they have a working group with that. We were talking about getting the CVs, the cataclysmic variables, but they are not in the continuum catalog because they have the emission line, so they're in the galactic catalog. So I can put you in contact with the galactic people, and then yeah, we can have some of their trash too. So yeah. Because I've seen some of them that look like AJ, and I was measuring like this is not a CV, but yeah, I have some.
You must have a huge trash bin.
It's a trash that is that sometimes we recycle, and I'm like, okay, let's put it back, and do it again. No, I've seen some. It was like no, this cannot be a CV. So yeah, I've seen some of them. Yeah,
It is the legend, the very thing.
I know, but yeah.
That is just a very tiny.
Any other question?
Redshift may help
Yes.
a little bit.
No. So then we can thank Barbara.
Thank-
Great. And has a question.
One more.
One more. Final question.
Final question.
When you showed the number, the luminosity function,
Yes,
mass function, are those only spectroscopic ones or photometric?
no, this is photometric, so they do the luminosity based on the photometry. And they count so this is basically the number of white dwarfs in each one of those bays.
No,
But,
Barbara,
yes,
it's showing old graph.
yeah, no, this is, okay, but this,
I have one with.
Yeah. I know, but that's an older one. I liked it. Yeah, I know, but I like this old one because it's less dependent on the volume, so you have to make sure that the major problem with those luminosity functions are the models of the galaxy. So you need to do a volume correction. Now, this is one thing which I learned in the past years, and I thought that it was very interesting. With Gaia, they were able to do the 40 parsec sample. So we have a volume limited sample of white dwarfs in 40 parsec. And that became like the gold standard for white dwarfs. And then they expanded to 100 parsec. And I remember getting bored in the white dwarf meetings and then thinking, actually, this has a very important result. We knew it already. We didn't learn anything new, which meant that our models were really good. So I was happy about that. I was bored, remember? Because I was like, why are they showing this again? But it shows how well we understood the models of our in the solar neighborhood around the 40 parsec and so on. So this is still a little bit, I mean, very dependent on the galactic model and the volumetric corrections and so on. But
¿Por escogiste esa forma tan gozada de poder arreglar más la luminosidad en hacer simple section?
eu não sei. Não, a sequência de esfriamento do Mestel da menos 5. This is theoretical. Yeah.
Radicals,
Pode isso ver.
this theoretical
Ah.
function.
Certo, mas digo, eso M sobre L
Yeah.
5 section.
Amplify that.
Digo, pode tem ser enganoso, por L 5 section, L na menos 5 section.
So again, let's thank Barbara.
Vamos continuar conversando.
No, Rafa, distorção no azul é um problema.